Good morning to everyone. In this video, we are going to start 5th unit in our subject power electronics, that is inverters. We mainly going to concentrate on what is inverter, that is concept of inverter, what are the applications of inverters, and what's the classification of inverters depending upon several factors, and we are going to concentrate on working of basic bridge inverters. Coming to concept of inverter, the concept of inverter is exactly opposite to the concept of rectifier. That is, in rectifiers, rectifier is a circuit which converts AC parameter to DC parameter. That is nothing but AC input to DC output. But in case of inverters, we are going to convert the DC input to the AC output. This is the representation of inverter. That is, it is a circuit which converts DC input to the AC output. This is the representation of DC parameter as well as this is the representation of AC output parameter. Okay, inverter is a circuit which converts this DC parameter to AC parameter is called inverter. In case of rectifiers, the process of converting the AC parameter to DC parameter is called rectification. In case of inverters, the process of conversion of DC parameter to AC parameter is called inversion. That is exactly opposite to the rectification in rectifiers. Coming to applications, inverters commonly used for getting the reliability in supply. That is, first application is in UPS, that is uninterrupted power supply. We are using the inverters, and second one is the HVDC transmission lines. In this also we are going to use the inverters for converting one input parameter to another output parameter, and industrial heating also we are going to use the inverters. And coming to main application, that is the speed control of AC drives. In this we are going to use the inverters for controlling the AC drives. These are the some of the main applications of inverters. We are having so many applications, but these are the main applications of inverter circuits. Coming to types of inverters, depending upon some parameters, we are going to classify the inverters. Those parameters are depending upon the type of the commutation, and depending upon the type of the source we are going to use, and third one is the depending upon the configuration. Here I think everyone know what is commutation. Commutation is nothing but the process of turning off the SCR is nothing but commutation. Means depending upon the type of the commutation we are going to use the we are going to classify the inverters. Similarly, I think everyone know source. That is, types of sources are two, that is current source and voltage source. Depending upon those sources we are going to classify the inverters. Similarly, we know type of configurations. We mainly having three configurations, that is first one is the bridge, second one is the series, and third one is the parallel. Depending upon those configurations we are going to classify the inverters. Coming to first classification, that is depending upon the type of the commutation. Depending upon the type of the commutation, the inverters are mainly classified into three types. That is, first one is the line commutated inverters, second one is the forced commutated inverters, and third one is the load commutated inverters. Okay, coming to first one, line commutated inverters. The inverters in which Thyristors present in the inverters undergoes natural commutation. Those type of inverters are called line commutated inverters. Similarly, coming to second one, that is forced commutated inverters. The inverters in which SCRs undergoes forced commutation. Those type of inverters are called forced commutated inverters. And coming to third one, the inverters in which SCRs commutated depending upon the type of the load. Those inverters are called load commutated inverters. This is the classification of inverters depending upon the type of the commutation. Coming to second classification, that is depending upon the type of the source we are going to use. Mainly we are having two types of sources. Those are, first one is the current source and second one is the voltage source. Depending upon these two sources, inverters are classified into two types, that is voltage source inverters and current source inverters. Okay, these are the concept of these inverters are very simple. Coming to voltage source inverters, the inverters which are fed with constant voltage source. Those inverters are called voltage source inverters. Coming to current source inverters, the inverters which are fed with constant current source, those are called current source inverters. This classification is very simple depending upon the type of the source. Coming to third classification, that is depending upon the type of the configuration we are going to use. Depending upon the configuration, inverters are classified into three types. This classification is very important. In 15th unit, we are mainly going to concentrate on this classification of inverters. That is, in that first one is the bridge type inverters. Okay, if the SCRs are connected in bridge configuration, those type of inverters are called bridge type inverters. Depending upon the number of SCRs, these bridge type inverters again classified into two types, that is half bridge inverter and full bridge inverter. In half bridge inverter, we are going to use 2 thyristors. In full bridge inverter, we are going to use 4 thyristors. We are going to discuss about working of these inverters. And second one is the series inverters. Okay, the inverters in which commutating elements, here commutating elements are nothing but inductor and capacitor. That is the inverters in which the commutating elements are connected in series to the load. Those type of inverters are called series inverter. And similarly, parallel inverter. Parallel inverter is exactly opposite to the series inverter. That is nothing but the commutating elements are connected in parallel to the load. Those type of inverters are called parallel inverters. Okay, these inverters are very important in 5th unit. That is depending upon the type of the configuration, bridge inverters, series inverters and parallel inverters. Bridge inverters, in this the SCRs are connected in bridge configuration. Depending upon the SCR, number of SCRs, these are classified into half bridge SCR, half bridge inverters and full bridge inverters. And depending upon the connection of commutating elements, series inverters and parallel inverters. In series inverters, commutating elements, that is nothing but inductor and capacitor, are connected in series to the load. And parallel inverters, the commutating elements are connected in parallel to the load. Okay, this is the classification of inverters depending upon several factors. That is depending upon the commutation, type of the commutation. Second one is the depending upon the type of the source we are going to use, and third one is the depending upon the configuration. Now we are going to discuss about working of bridge type inverters. The inverters in which the SCRs are connected in bridge configuration, those inverters are called bridge type inverters. Depending upon the number of SCRs, these are classified into two types, that is half bridge inverter and full bridge inverter. Now first we are going to discuss about working of half bridge inverter. Coming to circuit description, the circuit of half bridge inverter consisting of two SCRs, load, DC source. Here DC source is separated into two parts. This is the circuit diagram of half bridge inverter. It consisting of two SCRs, that is T1 and T2 are the two SCRs, and load and DC source. Here DC source is separated into two parts, that is Vs by 2 and Vs by 2. The working of this half bridge inverter is very simple. At a time only one SCR going to conduct. Okay, due to the conduction of those SCRs, we are going to get the output voltage across the load. Coming to working of half bridge inverter, the working can be explained in two operating modes. Consider first case. In this case, due to the application of these voltage sources, both the thyristors T1 and T2 are in forward blocking mode. Both are act as a open circuit before giving the gating pulse. In this case, we are going to apply the gating pulse to thyristor T1. Due to the application of gating pulse to thyristor T1 comes from forward blocking mode to forward conducting mode, and it acts as a short circuit, and we are not going to apply the gating pulse to thyristor T2. So thyristor T2 act as a open circuit, and due to the short circuit of thyristor T1, there is a path for current from source to load in the direction of Vs by 2 plus thyristor T1 terminal B, load terminal A, Vs by 2 minus, that is nothing but in this path. Total input voltage, this much of input voltage is going to appear across the load, that is V0 is equal to Vs by 2 plus Vs by 2. Coming to second case, that is at t is equal to t by 2, by using forced commutation, turn off the thyristor T1 and apply the gating pulse to thyristor T2. Due to the application of gating pulse to thyristor T2, it comes from forward blocking mode to forward conducting mode and it acts as a short circuit. Due to the conduction of thyristor T2, there is a path for current from source to load in the direction of Vs by 2 plus to terminal A load, terminal B T2 and Vs by 2 minus, that is nothing but in this direction. Total amount of input voltage going to appears across the load, that is V0 is equal to minus Vs by 2. Here negative sign indicates the opposite direction of current, that is in previous case current is flowing from terminal B to terminal A in this direction due to the conduction of T1. But in this case, current is flowing from terminal A to terminal B due to the conduction of T2. Okay, that is the current direction is opposite compared to previous direction. So we are going to get the voltage which is opposite to the previous voltage, that is in previous case we are going to get the plus Vs by 2. So in this case we are going to get minus Vs by 2. That is the working of Hybrid's inverter. Depending upon this analysis, where we are going to draw the output voltage waveforms. These are the output waveforms of Hybrid's inverter depending upon the analysis. Here Vs is the input voltage. This input voltage we are going to divide into two halves, that is plus Vs by 2, and here V0. This is the output voltage waveform. Okay, initially we are going to apply the gating pulse to thyristor T1. So thyristor T1 is in on state. Due to the conducting of thyristor T1, we are going to get the plus Vs by 2 as a output voltage. This is the plus Vs by 2. Again at t is equal to t by 2, by using forced commutation we are going to turn off the thyristor T1 and we are going to apply the gating pulse to thyristor T2. So thyristor T2 starts conducting. Due to the conduction of thyristor T2, we are going to get the output voltage as minus Vs by 2. Okay, this is the output voltage which is minus Vs by 2. Again at time t is equal to t, we are going to turn off the thyristor T2 by using forced commutation. Again we are going to apply the gating pulse to thyristor T1. So thyristor T1 starts conducting. Again we are going to get the plus Vs by 2 as a output. Similarly again at next interval we are going to turn off the thyristor T1 and we are going to apply the gating pulse to thyristor T2. So we are going to get the minus Vs by 2 as a negative voltage, as a output voltage. Okay, these are the waveforms related to Hybrid's inverter. By using these waveforms, we are going to obtain the average output voltage and RMS output voltage. That is nothing but characteristic parameters. Coming to characteristic parameters, by using waveform itself, we are going to find out the average values, that is average output voltage. If we consider time period from 0 to t by 2, we are getting the average voltage as plus Vs by 2, that is this thing, 0 less than or equal to t less than or equal to t by 2, we are going to get the output voltage is plus Vs by 2. Similarly, if we consider from t by 2 to t, we are going to get the minus Vs by 2 as the average voltage, that is nothing but this one, t by 2 less than or equal to t less than or equal to t is equal to V0 is equal to minus Vs by 2. These are the average output voltages from the waveforms. Similarly go for RMS voltage calculation. We already know the formula for finding the RMS voltage, that is square root of 1 by t integral 0 to t f of t square dt. Here f of t is nothing but function, that is Vs by 2 for 0 to t by 2 and minus Vs by 2 for t by t to t by 2 to t. Okay, substitute all those values here, then we are getting, that is from 0 to t by 2 we are substituting Vs by 2 as a function. Similarly from t by 2 to t. We are going to substitute minus Vs by 2. Okay, after substituting here 1 by t and Vs by 2 whole square as a common. By taking this one as common, we are having these are the remaining things, that is 0 to t by 2 into dt plus integral t by 2 to t dt. Okay, now apply the integration for dt in both the terms. Then by applying the integrations, we are getting the t. Okay, and we are having the different limits. In place of t, substitute these limits, that is coming to this term t by 2 minus 0 plus this term t minus t by 2. Here t by 2 minus t by 2 gets cancelled. After cancelling, we are having this term, that is 1 by t Vs by 2 whole square into t minus 0 whole power 1 by 2. Again t and t gets cancelled. Then we are having Vs by 2 whole square whole power 1 by 2. This 1 by 2, this square gets cancelled. Then we are getting Vs by 2 as the RMS output voltage for half bridge inverter. These are the calculation of characteristic parameters, that is average output voltage as well as RMS output voltage. These two are enough for inverters. Similarly, go for full bridge inverter. Coming to second type of bridge inverter is a full bridge inverter. The inverter which consisting of 4 SCRs is nothing but full bridge inverter. Coming to circuit description, it consisting of 4 SCRs, load and DC voltage source. In this case, we are not going to separate the DC voltage source. This is the circuit diagram of full bridge inverter. It consisting of 4 thyristors, that is from T1 to T4, which is supplied by DC voltage source Vs and having the load, and we are going to calculate the load output voltage across the load. Now coming to working, the working of full bridge inverter can be explained in two cases. Consider first case. In this case, we are going to apply the voltage source Vs to the circuit. Due to the application of voltage source, all 4 thyristors act as a open circuit. Why? Because due to the application of voltage source, all the thyristors are in forward blocking mode and act as a open circuit. Now we are going to give the gating pulse to thyristors T1 and T2 in the first case. Due to the application of gating pulses to thyristor T1 and T2, thyristors T1 and T2 coming from forward blocking mode to forward conducting mode and act as a short circuit, and remaining 2 thyristors, that is T3 and T4, act as a open circuit. And due to the conducting of T1 and T2, there is a path for current from source to load in the direction of Vs plus thyristor T1 terminal A, load terminal B, T2 and Vs minus. So total amount of input voltage is going to appear across the load as a output, that is current path is in this direction and total amount of input voltage is going to appear across the load, that is V0 is equal to minus Vs. That is the first case of full bridge inverter. Coming to second case of working, in this case at t is equal to t by 2, by using forced commutation, turn off the thyristors T1 and T2, and we are going to apply the gating pulse to remaining 2 thyristors, that is T3 and T4. By applying the gating pulse to these 2 thyristors T3 and T4 comes from forward blocking mode to forward conducting mode, and these two act as a short circuit. Due to the conducting of these 2 thyristors, there is a path for current from source to load in the direction of Vs plus thyristor T3 terminal B, load terminal A, T4 and Vs minus, and total input voltage going to appear across the load, that is V0 is equal to minus Vs. Here voltage appears as a negative. Why? Because in this case current is flowing from terminal B to terminal A, which is opposite to the current direction in the previous case. In the previous case, current is flowing from terminal A to terminal B, that is opposite to the previous case. So we are going to consider the output voltage that is opposite to the previous case output voltage. In previous case we consider output voltage V0 is equal to plus Vs. In this case we are going to consider the output voltage V0 is equal to minus Vs. Thus the working of full bridge inverter. By using this analysis we are going to draw the output waveforms. These are the waveforms related to above working. That is, here Vs is the input voltage and here V0 is the output voltage. Initially we are going to give the gating pulses to thyristors T1 and T2. So these two starts conducting. Due to the conduction of T1 and T2 we are going to get the plus Vs is the output voltage, which is same as the input voltage. Again at T is equal to T by 2, by using forced computation we are going to turn off these two thyristors and we are going to apply the gating pulses to T3 and T4. Due to the application of gating pulses to T3 and T4, these two starts conducting and there is a path for current from source to load and we are going to get the same input voltage as a output voltage, but we are going to get the negative voltage as a output. Why? Because the current direction is opposite to the previous current direction. So we are going to get this amount of voltage as a output voltage, which is negative. Again at T is equal to T, by using forced commutation we are going to commutate the thyristors T3 and T4 and we are going to apply the gating pulses to again T1 and T2. Due to the application of gating pulses these two starts conducting and we are going to get the positive output voltage. That is, this is the positive output voltage, which is same as the input voltage. Again at next interval we are going to turn off the T1 and T2. Again we are going to turn on the T3 and T4. We are going to get the output voltage which is same as the input, but we are going to get the negative output voltage. This is the working and waveforms related to full bridge inverter. By using these waveforms we are going to obtain the average output voltage and RMS output voltage. Those are nothing but characteristics of full bridge inverter. Coming to characteristic parameters, first one is the average output voltage. For finding the average output voltage we are going to use the waveforms. From the waveforms we are going to calculate the average output voltage. From time 0 to T by 2 we are going to get the plus Vs is the output voltage, which is same as the input voltage. So from 0 to T by 2 we are going to get the output voltage that is same as the input voltage plus Vs by 2. This is the average output voltage during the time period 0 to T by 2. Similarly from T by T to T by 2 to T we are going to get the output voltage is minus Vs. This is the average output voltage during the time period T by 2 to T. Okay, these are the average output voltages for different time periods. Similarly go for RMS output voltage. By using formula also we will get the same voltages as a average output voltages. Otherwise these are the simply direct, that is straight line. So by using waveforms itself we are going to consider the average output voltages. Similarly consider RMS output voltage. I think everyone know the formula for finding the RMS output voltage, that is square root of 1 by T integral 0 to T f of t square into dt. Here T is nothing but time period, that is equal to T, and f of x is nothing but function. We are having two functions for different time periods, that is from 0 to T by 2 we are having Vs as the function. Again T by 2 to T we are having minus Vs as the function. Substitute those two values in this expression, then we are getting these things, that is 1 by T Vs square integral 0 to T by 2 dt plus integral T by 2 to T, here minus Vs whole square means Vs whole square into dt. From these two terms take 1 by T into Vs square as common and then apply the integration and substitute the limit. By applying and substituting the limits we are getting these things, that is T by 2 minus T by 2. In this plus T by 2 minus T by 2 gets cancelled. Okay, after cancellation we are getting this expression, that is 1 by T Vs square t minus 0 whole power 1 by 2. Again here t gets cancelled. We are getting Vs square whole power 1 by 2. Again square and root will be cancelled. Then we are having Vs. Vs is the RMS output voltage for full bridge rectifier. In case of half bridge rectifier, we are getting Vs by 2 as the RMS output voltage. This is the working and output expressions for average voltage and RMS voltage for full bridge as well as half bridge inverters. Now I am going to give small problem for your practice on inverters. This is regarding introduction of inverters and working of half bridge as well as full bridge inverters. In the next video, we are going to discuss about series inverter as well as parallel inverter. These two are very important inverters in 5th unit. Thank you.